Welcome to the Deep Dive, the show where we cut through the noise and get straight to the insights. Today, we're plunging into a topic that affects absolutely everyone, from the largest corporations to the device in your pocket: cybersecurity.
Yeah.
It's a relentless, high-stakes battle, isn't it? We're constantly hearing about sophisticated attacks. Remember the Colonial Pipeline ransomware that crippled critical infrastructure, or the subtle, pervasive SolarWinds attack that went undetected for months?
Oh, yeah. Those are huge.
Yeah.
And they really highlight the challenge.
Security teams are genuinely drowning in a flood of data under immense pressure, and frankly, traditional methods are struggling to keep pace.
They really are.
It's becoming clear that we need a serious game changer.
You're absolutely right. The sheer volume and complexity of cyber attacks these days are just staggering. Manual efforts, even from the most brilliant, highly skilled professionals, are simply not enough anymore. It truly is an arms race. And without innovative tools, the defenders are at a significant disadvantage. This is precisely where artificial intelligence steps in, offering not just a glimmer of hope, but some incredibly powerful new capabilities.
Okay, so let's unpack this then. Today, our deep dive is into AI for cybersecurity, a handbook of use cases. Think of this as your personal masterclass, right? A comprehensive guide exploring how artificial intelligence is being applied to solve some of the most critical security problems out there.
Exactly.
Our mission as your instructors today is to walk you through this handbook, chapter by chapter. We'll extract the core insights, the practical applications, and the underlying methodologies that make AI such a powerful, transformative tool in the cybersecurity arsenal.
And what's truly fascinating here, and indeed the driving force behind this handbook, is the critical need for AI in cybersecurity. The authors highlight several key observations that really set the stage for why this technology isn't just a nice-to-have, but an absolute necessity.
So why exactly is AI so essential right now?
Well, the first big reason the handbook points out is about bridging what it calls the manual effort gap.
Right, that gap.
Think about something as complex as reverse engineering malware code. It still demands an immense amount of manual effort from highly skilled human experts.
Oh, absolutely. It's painstaking work.
These are people using specialized software tools. Imagine like IDA Pro as a high-tech X-ray machine for binary code, letting analysts see its inner workings, or GDB as a pause button and rewind feature.
Yes, stepping through execution.
Letting them step through a program's execution to understand its logic. It's incredibly labor-intensive work, and the industry has a massive incentive to leverage AI to drastically reduce that human-intensive labor, freeing up these brilliant minds for higher-level strategic work.
Precisely. And this directly connects to a second crucial point: enhancing accuracy in classification tasks. We're talking about really important security functions like malware classification, just identifying if a piece of software is malicious or not.
Or classifying network traffic at a session level. Traditional methods often fall short, struggling to achieve the desired accuracy needed for robust, proactive defense.
So they miss things or flag the wrong things.
Exactly. AI offers a clear path to significantly improve this accuracy, providing more reliable, faster, and ultimately more trustworthy detection.
Now, here's where it gets really interesting and impactful. The third reason highlights AI's essential role in supercharging cyber operations. Picture an enterprise system. It's vast networks, diverse platforms, countless applications, files, and databases, all relying on security teams to defend against a constant barrage of known and unknown threats.
It's a huge attack surface.
These teams are always trying to answer four fundamental questions: what happened? What's the impact? Why did it happen? And perhaps most critically, what should be done about it? But as we've seen with major incidents, these teams face severe limitations.
They certainly do. One major limitation is simply slowness. Human cognition bottlenecks when faced with the sheer fire hose of cyber data that bombards security operations centers daily.
Just too much information.
Way too much. Then there's often a lack of the big picture. Isolated, stovepiped organizational processes can prevent a holistic view of a developing threat.
Like different teams not talking to each other.
Precisely. You also encounter outdated mindsets, such as unrealistic trust assumptions, which, as the SolarWinds attack tragically demonstrated, can be incredibly harmful.
Assuming something is safe when it isn't.
Right. And finally, there's a serious human resources gap, with a vast performance difference between junior and expert analysts. This is where AI technologies, particularly deep learning, offer exciting opportunities. Accurate threat detection and prediction, improved agility, reduced costs, enhanced analyst performance, and a much higher level of automation.
Companies are already seeing this in action, with AI powering sophisticated security solutions.
And a fourth powerful observation is that even highly successful existing security tools can benefit substantially from AI. Take fuzzing, for example.
Yeah, fuzzing is a good one.
It's a standard and effective security testing technique, great for finding vulnerabilities. But its efficiency can still be a concern. AI can significantly improve that efficiency, making these tools even more powerful and faster at uncovering weaknesses before attackers do.
So what does all this mean for you, whether you're looking to build one of these systems or just understand the landscape better? This handbook isn't just another research summary. It's a truly hands-on guide designed for engineers, security analysts, and students.
Right.
Its unique value is providing a jump start for beginners, offering practical, concrete use cases for experienced professionals.
Exactly. Instead of lengthy general principles, each chapter focuses on a specific problem and its AI-driven solution presented in a straightforward way. This means you can easily navigate to the areas you're most interested in, even if it's just, conceptual understanding. It covers the entire machine learning pipeline, from raw data collection all the way to deployed models, giving you a real-world learning experience. It really promotes learning by doing, by providing practical examples, and you can use it to gain a solid understanding of how AI is genuinely applied in cybersecurity today.
This leads us to a foundational concept within the handbook: the unified deep learning pipeline. Think of this as the underlying blueprint for many of the use cases we'll explore.
Okay.
Even though cybersecurity problems are incredibly diverse, the application of deep learning often follows a standardized, systematic approach. This pipeline will be a recurring theme, helping us connect disparate topics and understand the common thread that runs through these AI-driven solutions. It's a structured way to approach complex problems.
Okay, great. So let's begin our first deep dive into the specific applications then. We're starting with Chapter 2, which shows how AI conducts two critical reverse engineering tasks.
Right, reverse engineering, or RE. It's a foundational process in cybersecurity.
Hmm.
At its heart, it's about recovering semantic information. Think of it as the original source code logic from binary files.
The actual machine code.
Exactly. This is absolutely essential because, as you can imagine, commercial software rarely provides its source code. And malicious software, or malware, certainly doesn't. So reverse engineering is critical for understanding and analyzing malware.
And it really matters for deploying robust security strategies too, right? For instance, to implement advanced defenses like control flow integrity on programs where you only have the binary, you need RE to uncover the hierarchy structures within that binary.
You need that map.
Or if you're analyzing ransomware, to find those elusive crypto keys or understand how it evades detection, analysts first need to generate flow graphs of the ransomware, which often involves battling heavy obfuscation designed to hide its true intentions.
The human challenge here is immense. Manual reverse engineering is incredibly labor-intensive. An analyst painstakingly has to guess where functions start and end, trace the flow of control and data, infer the meaning of data,
Just trying to piece it all together?
and then somehow aggregate all this information into a holistic understanding of the program's logic. This is precisely why there's such a strong incentive for automatic RE methods powered by AI and deep learning.
So the handbook focuses on two core RE tasks that AI is tackling. First, function boundary identification.
Okay.
Imagine you have a raw sequence of bytes from a program's executable section. The goal is to detect precisely where functions begin and end within that stream of data.
Right, like finding paragraphs in a book with no punctuation.
Exactly. The challenge is, without clear markers, it's like trying to find where sentences start and stop in a stream of letters with no spaces or punctuation.
And the second task is function signature generation. Here, once we've identified a function's boundaries, AI steps in to predict its return type, how many parameters it takes, and the type of each of those parameters.
That sounds straightforward, but it's not.
Well, while these tasks might sound simple, they're surprisingly difficult because compilers, the tools that turn human-readable code into machine code, can emit binary, incredibly hard-to-predict patterns. It's not a straightforward translation.
Okay. Now, if we look at how this compares to traditional methods, historically, tools like IDA Pro have been widely used by security analysts to make sense of binaries. These tools are powerful, built on extensive human-derived rules and domain knowledge about how code is typically generated.
However, these traditional rule-based tools have significant limitations. The binary code produced can vary drastically depending on the programming language, the specific compiler and its optimization settings, and even the target computer architecture.
Lots of variables.
Huge variables.
Crucially, the rise of obfuscation techniques used by commercial software to protect intellectual property or by malware to evade detection makes maintaining these rule-based methods an incredibly difficult and labor-intensive task. They simply can't keep up.
That's why the emergence of machine learning, and especially deep learning, has shown such big potential. Researchers have observed that deep learning excels at representation learning. It can discover intricate patterns in the structures in high-dimensional data that would be invisible to simpler methods. And while deep learning typically craves large data sets for training, this isn't a significant barrier for most reverse engineering problems, as a wealth of open-source code and binaries are readily available.
Which brings us back to that unified deep learning pipeline we mentioned.
Right.
We're seeing how RE tasks, despite their specific differences, share common characteristics, allowing for a systematic deep learning approach, starting with how we get and prepare the data.
So it all starts with the raw data. For reverse engineering, we're typically dealing with stripped binaries, that is, executables without any debugging information.
Right, no helpful hints left in.
But collecting this raw data isn't a hurdle at all. The beauty is that both binaries and their corresponding source code are widely available from various open source projects. This means researchers can easily generate large, diverse data sets by compiling the same source code with different compilers and optimization settings.
Okay, so you have the raw stuff. Once we have the raw binary data, the next critical step, discussed in the handbook, is beta annotation. This is about establishing the ground truth for our models.
Giving it the answers to learn from.
Exactly. A big advantage in reverse engineering is that this ground truth can often be obtained directly from the source code itself. During training, we assume the source code is available. This high-level information, like function names or variable types, can then be used to label the corresponding binary code.
Okay.
If the AI learns from these labeled examples, and then later, the trained models can process binaries without source code.
Got it. With our data collected and labeled, we move to data processing. This stage involves extracting the instruction sequences from the binary files. But the core challenge here is a fundamental one.
Right.
How do we represent these raw binary instructions in a way that a deep learning model can actually understand and learn from? It's like teaching a machine to read the code.
Yeah, how do you feed it bytes? There are a few key approaches here, each with trade-offs. The simplest is raw byte encoding.
Just the raw numbers.
Right, you just feed the machine code bytes directly into the AI. It's straightforward and avoids the complexity of disassembling the code. But the semantic meaning is largely hidden. The AI is looking at a stream of numbers without much context. Can a neural network truly learn deep meaning from just this? It's questionable.
So a step up from that is encoding of disassembled instructions.
Right.
Here you first disassemble the machine code into assembly code, which is much more human readable and carries more semantic meaning.
Like MOV, AX, BX.
Exactly. Then you extract features like the operation codes or the operands. This gives the AI more comprehensible signals, but it still relies on some human-designed feature selection.
Which can be tricky. The most powerful approach, arguably, is representation learning for instructions. This is where the AI automatically learns its own vector representation, or embedding, for each instruction. It essentially teaches itself how to understand instructions.
Learning the language of code.
Pretty much. For example, some models can learn the latent semantic relationships between tokens within an instruction, making them more resilient to things like code obfuscation. This approach is powerful because it avoids manual, error-prone design and learns higher-level, less syntactic features.
But even with representation learning, things get complex, especially for intricate instruction sets like by 86. That's why the handbook highlights the benefit of pre-trained models for instruction embedding.
Right, leveraging prior knowledge.
These models are trained on massive, often unlabeled data sets through specific tasks to understand structures and semantics. Think of it like a human learning a language from millions of sentences before trying to write poetry.
That's a good analogy.
Once pre-trained, these models can then be quickly adapted for many specific downstream tasks, saving huge amounts of time and computational resources.
So if you're looking to build one of these systems, the guiding principle is this. If a suitable pre-trained model is available, that's often your best bet.
Makes sense.
If not, and you have ample training data and computational power, then letting the AI learn its own representations through representation learning is the next strongest option. If resources are limited, then encoding disassembled instructions can be a practical fallback. It's about smart choices based on your constraints and goals.
Okay, that clarifies the data side. Let's move on to the AI brain itself. The model architecture. Deep learning models for most reverse engineering tasks often share a common component. They need to learn rich representations for instruction sequences. How you represent that data truly dictates what the AI can understand.
To effectively capture the complex internal formats of instructions, some methods consider each instruction as a sentence within a code sequence and then break it down into basic tokens, like individual words.
Okay, breaking it down.
Yeah. A transformer model, which is very powerful for language tasks, can then be used to learn sophisticated embeddings for these tokens. This involves pre-training tasks to help the neural network understand instructions, such as predicting masked tokens to learn internal structure.
Like fill in the blanks for code.
Exactly. Or predicting context to understand control flow relationships, and even predicting data dependencies. These pre-training tasks help the AI build a deep understanding of what individual pieces of code mean and how they relate.
Once you have these powerful instruction embeddings, these understood representations of individual code pieces, some tasks become surprisingly straightforward. For function boundary identification, for example, a relatively simple output layer in the neural network can then predict whether each instruction represents the start or end of a function.
So the heavy lifting is in the embedding.
Right. It's like having a finely tuned sensor for function demarcation.
And for function signature generation, a similar approach is used. The pre-trained model generates embeddings for all instructions within a target function. Then, a recurrent neural network, like an LSTM or GRU, takes these instruction embeddings and aggregates them to form a single comprehensive understanding of the entire function.
Kind of summarizing the function's meaning.
Exactly. Finally, another output layer uses this aggregated information to predict the function's type signature, including its return type and parameters.
Of course, no machine learning journey is without its challenges. The handbook outlines some key model training issues. First, training these sophisticated pre-trained models can require substantial computing resources, particularly powerful GPUs, which can be a significant barrier for many.
Yeah, getting access to that kind of hardware isn't always easy.
Secondly, data sets can often be extremely imbalanced. For instance, in function boundary identification, a function with thousands of bytes might have only one start byte and one end byte.
Right, most bytes are just inside.
The AI sees far more inside of function examples than start-end examples. Solutions involve either carefully balancing the data or using special weighted loss functions to make the AI pay more attention to the rarer but more critical examples.
Giving more weight to the important stuff.
And a classic machine learning challenge applies here too. The precision versus recall trade-off.
It's always a balancing act.
Depending on the security problem, you might prioritize finding all possible malicious code, high recall, even if it means some false alarms, or you might prioritize only flagging definitively malicious code, high precision, to avoid disrupting operations. This trade-off can be tuned during training.
When it comes to model performance, these deep learning approaches show really impressive results. For tasks like function-type signature generation, representation learning models have demonstrated significant improvements over traditional handcrafted methods, often achieving accuracy levels well into the high 80–90% range.
That's pretty good.
Very good. Similarly, for function boundary identification, models can achieve very high precision and recall, meaning they're both accurate in what they identify and thorough in not missing many functions. These numbers are a strong testament to the power of learning rich representations.
Once trained and evaluated, the next step is deployment. There are two main ways to get these reverse engineering models into the real world. One is to integrate them directly into existing reverse engineering platforms like ID Pro.
Oh, as a plugin, maybe.
However, a challenge here is that these powerful pre-trained models can be quite large, demanding substantial computational resources that individual analysts might not have readily available on their machines.
So a more practical solution, especially for organizations, is to deploy these models as an online service. A company can host the model and its data processing components on a powerful cloud server.
Okay, cloud-based analysis.
Right. Users then upload the binaries they want to analyze. The server processes them, makes its predictions, and sends the results back. This offloads the heavy computational burden from the individual analyst's machine, making the power of AI accessible to many.
Now let's look at the road ahead for AI in reverse engineering the remaining issues. One key limitation with existing deep learning models for RE is their generalization ability.
Yeah, that's a big one.
A model trained on one platform often struggles with binaries from other platforms, different compiler tools, or even varying optimization levels. Think about the sheer diversity. Different processor architectures, multiple compilers, each with multiple optimization settings.
It's a combinatorial explosion.
Training a separate model for every single combination is incredibly resource intensive. Improving a model's ability to generalize across these variations is a crucial area of research.
A second limitation concerns the complexity of RE tasks. While current deep learning applications show great promise, they're primarily used for what we might call simpler RE tasks. More complex analyses, like generating complete control flow graphs or deeply understanding how data moves through a program, remain challenging.
Why is that?
The main reason is that current AI schemes aren't yet fully capable of learning truly high-level semantic information from binary code. Fortunately, researchers are increasingly pushing the boundaries in this area.
And finally, there is a subtle but important issue of code and data intermixing. Binary files often contain both executable code and static data, and sometimes, due to how computers fundamentally work, these can even be intertwined, for example, in complex jump tables.
Right, data embedded right in the code stream.
However, current deep learning applications in reverse engineering mostly focus on analyzing just the code. Learning to interpret the memory layout and actual data structures within a binary is still a largely underexplored area that offers significant research opportunities.
Okay, so moving on to Chapter 3, we shift our focus to a very tangible and pervasive threat that affects millions of people: AI detecting Android malware.
Section 3.1 really frames the security problem here. What is Android malware? Simply put, it's any malicious software viruses, trojans, ransomware, adware, spyware, phishing apps designed to harm your Android mobile device.
And the consequences can be serious.
Oh, yeah. These can steal your sensitive information, secretly spy on your calls and messages, or even demand ransom for your data, making your phone unusable.
These threats spread through various channels, from malicious downloads and emails to suspicious websites or unknown links. And while sideloading apps carries obvious risks, official app markets like Google Play and the Amazon App Store are still the primary distribution channels.
Right, most people get apps there.
Before an app is published, it undergoes analysis by the app market to detect maliciousness. This is a critical point where AI can make a significant difference in protecting users.
Here's a specific example that really highlights the ingenuity of attackers. The handbook shares an Android ransomware case where, in the past, ransomware would often just misuse a specific permission to draw full-screen ransom notes, locking you out.
Yeah, the system note window permission, that was common.
But a newer variant emerged, cleverly leveraging what appear to be call notifications and a specific programming method to continuously trigger its ransom screen.
How did that work?
The trick was sophisticated. The malware would create a notification that looked like an incoming call, triggering an immediate user action. Then, to continuously occupy the screen, it would override a callback function in its activity that normally triggers when an app is pushed to the background.
Ah, on user leave hin.
Right. This made the ransom screen automatically pop back up, creating a continuous loop of screen occupation that bypassed basic detection methods. It's a clever bypass that shows how quickly attackers adapt.
This particular use case is interesting because it doesn't rely on deep learning, but rather a robust machine learning pipeline.
Right, not just deep nets.
It highlights that AI for cybersecurity isn't just about deep neural nets. Traditional ML techniques are incredibly powerful too. The system we're looking at, called API Checker, is designed specifically for Android malware detection.
Okay, API Checker. How does it work?
The process generally begins by extracting metadata from an app through a dynamic analysis engine. This engine, often running in an emulator, collects crucial information like permissions, the app requests, the APIs it invokes, and the intents it uses to communicate with other apps.
So it runs the app safely and watches what it does.
Exactly. To make sure it covers all bases, it even simulates user interaction, like tapping buttons using something like the Monkey UI exerciser to get the app to expose as much of its behavior as possible.
Then comes feature engineering, which is all about crafting the right signals for our machine learning models. Instead of looking at raw, complex data, the system selects a key API set for encoding.
Focusing on important actions.
Right. These API invocation logs are then transformed into numerical feature vectors. These vectors become the training data for the machine learning component, which in this case uses a random forest algorithm.
After validation to ensure the model is robust, the trained model is put into production for online testing. A crucial part of this pipeline is system evolution. False positives and false negatives, mistakes by the model, are continuously collected.
Learning from its mistakes.
Precisely. This information then informs regular model retraining, typically monthly, allowing the system to adapt to evolving malware threats and new Android APIs.
Section 3.4 delves into feature engineering, which is truly critical for any machine learning task. In ML, a feature is an individual measurable property or characteristic, usually numeric.
Picking the right features is key.
Choosing informative, discriminating, and independent features is crucial for effective algorithms. In this context, APIs, application programming interfaces, are chosen as features. If an API is called when an app runs, its feature value is 1, otherwise it's 0. Like sending an SMS, that's an API call.
The challenge here is the sheer volume. The Android SDK has over 50,000 APIs. Tracking all of them is not only inefficient, but can actually reduce accuracy.
Too much noise.
Exactly. The handbook's authors demonstrated that only a small, carefully selected portion of these APIs, specifically 426 key APIs, are truly needed. Why? Because selective tracking reduces dynamic analysis time, improves detection accuracy by focusing on the most informative APIs, and allows for combining complementary APIs to build a stronger signal.
So how exactly do they choose these 426 key APIs? It sounds like finding needles in a haystack.
It's a clever multi-step strategy. First, they identify APIs with the highest statistical correlation with malware, meaning APIs whose usage strongly indicates malicious behavior.
Okay, which ones are most common in bad apps?
Right. Second, they select APIs that require restricted permissions, which are often exploited by malware to gain sensitive access, like reading contacts or location.
Things that need user approval.
Third, they identify APIs that perform sensitive operations based on expert knowledge of past attack vectors, things known to be abused.
Got it. Correlation, permissions, known bad operations.
Finally, they combine these three sets of APIs. This creates a robust and comprehensive set of 426 key APIs, leveraging different angles of malicious activity. This combined approach ensures they're not missing crucial signals while still keeping the feature set manageable and efficient.
But attackers are cunning, and malware can sometimes bypass direct API invocations using mechanisms like Java reflection or intents. How do they handle that?
Good point. To counter these concealed API invocations, the team further enriches the feature space by adding two auxiliary features: the requested permissions and the used intents.
So even if the API call is hidden, the permission still has to be there.
Precisely. The reasoning is that even for hidden APIs, an app still needs to request permissions from the operating system. This addition significantly improved detection performance, boosting both precision and recall.
Okay, so once these features are engineered, we move to the training data. The data set for this system comprised over 500,000 new and updated apps submitted to a major app market.
That's a lot of apps.
Crucially, each app was labeled as malicious or benign by the market's own analysis, providing the accurate ground truth needed for the machine learning model to learn. These API invocation statuses are logged and then converted into binary feature vectors, where a 1 indicates an API was invoked and a 0 otherwise.
The specific machine learning algorithm used is the random forest classifier. Think of a random forest as an ensemble learning algorithm that combines many decision trees.
Right, like asking a series of questions.
The decision tree is like a flowchart. You ask a question about a feature, and based on the answer, you follow a branch until you get to a classification. The strength of random forest is its ability to effectively reduce overfitting, meaning it doesn't just memorize the training data.
How does it avoid overfitting?
It does this by training multiple trees on slightly different subsets of data and then having them vote on the final classification, leading to a much more robust and accurate prediction.
Okay, so the wisdom of the crowd, but for decision trees.
You got it. Once trained, the model needs to be deployed. The API checker system has been running in production since March 2018, demonstrating its maturity and real-world applicability. It's capable of checking around 10,000 apps daily using a single commodity server.
That's impressive scale.
The process is efficient. An app's file is installed on an idle Android emulator, run, and all necessary information for feature engineering is logged. Then the random forest classifier makes its determination. This entire process is quick, taking only a couple of minutes per app.
And the results. How well does it work in practice?
The results speak for themselves. In its first year of operation, API Checker detected thousands of suspicious apps every month, consistently achieving very high precision and recall, meaning it accurately identified malware and didn't miss much. This real-world deployment on a massive scale really highlights the effectiveness of this AI-driven approach.
Even with robust deployment, the threat landscape never stands still. This leads to the necessity of system evolution.
Right, got to keep it updated.
The system requires periodic updates, typically monthly, to its selected key APIs. Why? Because new apps are constantly being added to the market, and the Android SDK itself undergoes regular updates, introducing new APIs. The system needs to continuously adapt and refresh its understanding of what constitutes malicious behavior to stay effective.
Makes sense. The goalposts are always moving. Okay, let's explore Chapter 4 now, where AI takes on the fascinating challenge of detecting abnormal events in sequential data.
This sounds interesting, like finding anomalies in logs or network traffic.
Exactly. This is where things get really intriguing, moving into predicting the unexpected before it becomes a full-blown crisis. Anomaly detection is broadly applied across industries for enhanced security. It involves identifying unanticipated changes or subtle deviations from what's considered normal behavior.
Okay.
In the context of an intrusion detection system, for example, it's about suspecting and anticipating attacks by flagging unusual outliers in a stream of observed events.
We're talking about sequential data here. Imagine a stream of network activities or system log entries over time. Anomaly detection operates on two basic assumptions. First, truly abnormal event subsequences are very rare within normal behavior.
Needle in a haystack again.
And second, their characteristics often differ significantly from normal events. The ultimate goal is to identify those anomalous time intervals, those unusual subsequences of events, within a larger stream of data.
For this kind of analysis, researchers use large data sets from real-world systems. One example is the UNSW NB15 dataset, which is a hybrid of real normal network activities and synthetic attack behaviors.
Okay, real and fake data mixed.
Right. Another is the SOSP 2009 log dataset, which contains millions of log entries from a Hadoop file system, manually labeled as normal or abnormal by experts. These diverse datasets provide the raw material for AI to learn what normal looks like and, more importantly, what abnormal signals an attack.
Now, let's consider data processing, how we prepare the sequential data for AI. For system logs, the raw entries often contain verbose text.
Yeah, logs can be messy.
A crucial step is refining these log keys, for instance, by attaching add-on strings that provide more context. So a generic log entry like received block might be enriched to a received block of size 2030 millibit from 10.250.
And adding that crucial context.
This adds more semantic meaning to each event, making it easier for the AI to understand. For network data, it involves extracting key fields like IP addresses and ports and combining them into discrete events that form a sequence.
Okay, so you structure the raw data. Now, for the brain behind the operation, the model architecture, specifically a bidirectional LSTM for anomaly detection.
LSTM, long short-term memory, right? Good for sequences.
Exactly. This approach is actually inspired by how we process human language, treating discrete events in logs or network flows as words and entire sequences of events as sentences. A traditional strategy might try to predict only the next event in a sequence. If the prediction is wrong, it's an anomaly.
Seems logical, but maybe too simple.
Well, this traditional forward-looking strategy has a limitation. It doesn't fully exploit the characteristics of a sequence because an operation isn't just affected by previous events, but also by later ones.
Context matters both ways.
Right. Think about solving a puzzle. Sometimes you need to see a piece further down the line to understand the one you're currently holding. This is why a bidirectional LSTM model is proposed for higher accuracy. It processes the sequence in both forward and backward directions, allowing it to see the full context.
Okay, so it looks both ways down the sequence. How does that work structurally?
This bidirectional model typically consists of four major components. First, an embedding layer translates the discrete event sequence into a numerical representation the AI understands.
Similar to the RE chapter.
Second, a deep LSTM autoencoder analyzes this representation and tries to reconstruct it, learning the underlying patterns of normal behavior. Third, an event classifier then takes the autoencoder's output and determines the likelihood of each event being a specific type. And finally, an anomaly critic compares these probabilities to the actual events, making the crucial call, normal or abnormal.
The power of this approach, particularly the bidirectional nature, is that the embedding layer doesn't just treat events as isolated words, it learns context. And the deep LSTM autoencoder aims to reconstruct the meaning of these events from the embedding layer rather than just simple data.
Right, it learns the normal structure.
This makes identifying time-sensitive anomalies more like detecting unfitting words in a sentence than just spotting numerical deviations. The anomaly critic then uses this rich understanding to flag events whose predicted probability is simply not among the most likely, signaling something unusual.
Moving to model deployment, the ideal scenario is for these models to determine whether an event or sequence is abnormal in real time. This is a critical challenge.
Yeah, detection needs to be fast.
Meeting real-time requirements demands adequate computational resources, CPU, GPU, and memory. Tools like containerization, using Docker, are useful here, making scaling and updates easier. And if these models need to run on-edge devices like IoT sensors or industrial controls, a lightweight execution environment, such as TensorFlow Lite, is required due to latency, privacy, and power constraints.
Okay, different deployment needs. How well do these bidirectional models actually perform?
When we evaluate these models, a bidirectional approach consistently shows superior performance. Compared to models that only look forward, models like Dablog achieve significantly higher accuracy in F1 scores, and crucially, they maintain better precision, fewer false alarms, and recall fewer missed attacks across a wider range of scenarios.
So the bidirectional part really makes a difference.
It really does. The why behind this superior performance lies in the benefit of the bidirectional LSTM. Single-direction models struggle with structurally abnormal sequences that rely on bidirectional causality. For example, an event deep in a log might only become truly suspicious because of an event that appears later in the sequence, which a forward-only model can't foresee.
It misses the punchline, essentially.
Exactly. The bidirectional nature allows the AI to foresee connections and causal relationships across the entire sequence, detecting subtle, sophisticated anomalies that would otherwise be missed. It means anomaly detection needs to see sequences as atomic instances and examine both structure and bidirectional causality to be truly effective.
Fascinating. For those eager to explore further, the handbook points out that the code for these anomaly detection systems is often publicly available.
Yeah, good for learning by doing.
And beyond autoencoders, other sequence reconstruction solutions, such as combining predictions from different directions, can also work well. There are also comprehensive datasets available like LogHub, which provide large collections of log abuse for research.
Interestingly, combining different models can further enhance performance. For instance, intersecting the outputs of two models, perhaps one looking at short sequences and another at longer ones, can significantly reduce false positive rates, improving the overall deep learning performance.
One challenge in the embedding layer is handling unknown event keys. What happens if the AI sees something completely new?
That's a good question. If an event key isn't in the training data, it's often treated as unknown, potentially misjudged as an anomaly, leading to high false positives.
Right, just because it's new doesn't mean it's bad.
Solutions include trying to add rare events to training data or leveraging pre-trained embedding layers that can map even novel events to meaningful representations.
Let's move on to Chapter 5 now, where AI takes on a classic and particularly insidious network threat, detecting DNS cache poisoning attacks.
Ah yes, DNS poisoning. Section 5.1 lays out this critical security problem. At its core, the domain name system, or DNS, is the Internet's phone book, providing the mapping between human-readable domain names and machine-readable IP addresses.
Right, turning google.com into an IP address.
Exactly. When your computer needs to contact a website, it queries a local DNS server to resolve the name to an IP. If the local server doesn't have the record, it queries a global DNS server.
To reduce latency and cost, local DNS servers cache common mappings. This is precisely where the vulnerability arises.
The cache.
When your local DNS server asks a global one for an uncached domain, the critical point is that the local DNS server cannot verify the response. An attacker can send a spoofed response with a falsified record before the real one arrives. Your local DNS then caches this falsified record and forwards it to you.
And boom, you're directed to the attacker server instead of the real one.
And once that falsified record is cached, all subsequent queries for that domain will receive the incorrect IP address until the cache expires or is flushed. This is DNS cache poisoning. It's incredibly difficult to detect with traditional signature or rule-based intrusion detection systems.
Either?
Because the attack packets are intentionally crafted to follow protocol and look exactly like genuine DNS packets. They blend in perfectly.
Indeed. The fact that it's a session-based attack, requiring information from multiple packets across a conversation, makes handcrafting features for traditional methods a daunting barrier. This is precisely why deep learning is applied here. It can learn these complex session-level patterns automatically.
Section 5.2 discusses raw data generation and collection. Interestingly, for this specific attack, there wasn't a publicly available data set that accurately represented real-world DNS cache poisoning in all its variations.
So they had to make their own.
Exactly. The authors generated their own raw data, both benign and malicious, by leveraging protocol fuzzing.
Fuzzing. Throwing unexpected data at things.
Kind of. Protocol fuzzing for data generation is incredibly useful here. It allows for the rapid generation of a wide variety of malicious network packets specifically tailored for chosen attacks. Crucially, these generated packets can be automatically labeled as malicious, significantly cutting down on manual effort.
And it probably creates weirder attacks than you might see normally.
Right. It also produces data with more variations than you might see in limited real-world captures, including unforeseen scenarios, ensuring the model is robust.
The testbed setup is straightforward. A local DNS server, a user machine, and an attacker machine. In the malicious scenario, the user queries an uncached domain from the local DNS. The attacker sniffs these queries and then sends fuzz DNS responses, spoofing the global DNS server with falsified IP addresses.
Racing the real response.
The local DNS server's cache is periodically flushed to ensure it remains vulnerable. Success is verified by observing that the user's queries return the falsified IPs. For the benign scenario, the user simply queries legitimate domains, with the cache still being flushed periodically to simulate uncached lookups.
Section 5.3 addresses labeling DNS sessions. The goal is to train a deep learning model to classify entire DNS sessions as malicious or benign.
Labeling the whole conversation.
Since this is a session-based attack, labels are assigned per session, typically marked by the user's initial DNS query packet. If a session leads to a successful DNS cache poisoning attack, it's labeled malicious. Otherwise, it's benign. A convenient aspect here is that malicious and benign raw data were collected separately, which simplifies the labeling process.
Moving to feature extraction and data sample representation in Section 5.4 is about crafting AI-friendly input. Simply feeding the whole packet intuitively seems like a good idea, but it's actually problematic.
Why not use the whole thing?
Firstly, packets can contain sensitive private information. Secondly, the model might learn unintended signatures, like specific MFI addresses, instead of the actual attack characteristics, making it brittle.
Learning the wrong patterns.
So instead of the whole packet, only specific relevant bytes are chosen from each DNS packet. Crucially, the Ethernet layer is often omitted to exclude MC addresses, and parts of the IP, UDP, and DNS layers are included.
Just the relevant protocol parts.
Right. Important sections like the query and record sections are typically excluded to prevent the model from learning malicious domain names, making it focus on the structure of the attack rather than specific content.
Okay. Initially, each selected packet segment becomes a fixed-length sequence of bytes. The entire captured traffic is then a long sequence of these byte representations. This long sequence is then chopped into individual sessions, with each user DNS query marking the start of a new, potentially variable-length session.
To unify this data representation for the deep learning model, the variable length sessions need to be processed into fixed-length ones. One common method is using sliding windows.
Like looking at chunks of the conversation.
This converts long sequences into several shorter fixed-length sequences, each representing a slice of the session, ready to be fed into the network.
The final crucial step is transforming these bytes into bits. Why bits? Because the numerical difference between byte values doesn't always reflect a functional difference.
Like flags in the DNS header.
Exactly. For example, two DNS flags might differ by only 1 bit functionally, but by a large numerical value. A bit representation is more natural for the AI to understand the fine-grained nuances of protocol fields. So bytes are transformed into 8-bit sequences.
And the final data samples end up looking like small, three-dimensional images, with dimensions representing packet index, byte in packet, and bit in byte, which are then labeled as malicious or benign.
Interesting. So network traffic becomes an image. For dataset construction, before training, tests, and validation sets are created, 2 types of problematic samples are removed. First, double-dipping samples, identical data points appearing in both benign and malicious classes, are discarded as they don't aid classification.
Useless data.
Second, duplicate samples within the same class are reduced to appear only once, preventing bias from overrepresenting certain examples. After these removals, the dataset is balanced to ensure both malicious and benign examples are well represented.
Given that the data samples are effectively image-like, model architecture naturally leads to the choice of a convolutional neural network, or CNN.
Makes sense for image data.
CNNs have proven highly effective in computer vision for processing such structured, multidimensional data, making them ideal for discerning patterns in these packet images. The architecture typically includes several layers of convolution, pooling, and fully connected layers, culminating in an output layer for classification.
When it comes to model deployment, it's crucial to remember that the training environment often differs significantly from the deployment environment. Production systems prioritize efficiency and cost, meaning different computational speeds, memory, and network bandwidth.
Right, labs are different from the real world.
So models typically require additional optimizations before they can be deployed effectively in the real world.
This is where techniques like post-training quantization come in handy. It's a conversion technique that drastically reduces a model's size and improves its latency on CPUs and hardware accelerators, often with minimal degradation in accuracy.
Making the model smaller and faster.
Exactly. The simplest form statically quantizes model weights, from floating point numbers to 8-bit integers. Further optimization can involve dynamically quantizing activations during inference, achieving near-full fixed-point inference speed. The impact can be significant, reducing model size dramatically and making it feasible for real-world production.
Looking at remaining issues for this use case, there's always a need for further runtime efficiency optimization. While quantization helps, the underlying deep learning model and its library dependencies can still be resource-hungry to load.
Yeah, TensorFlow can be big.
And the multi-step data processing pipeline, which converts raw packets into image-like data, is also computationally intensive, so optimizing this aspect is crucial for real-time performance.
Second, model updating is a continuous challenge. This use case focuses on a single iteration, but in a real-world scenario, new data is constantly observed after deployment, leading to an increase in labeled data.
Need to keep learning.
The simplest approach is to periodically retrain the entire model with this new data, evaluate it, compare it to the old one, and replace it if the new model performs better, ensuring the system stays current with evolving threats.
Let's move on to Chapter 6 now, where AI takes on the monumental task of detecting PC malware. This is a battleground that's constantly shifting and evolving, with attackers perpetually trying to evade defenses.
Oh yeah, PC malware is a huge area.
Yeah.
Section 6.1 highlights the escalating malware threat. Traditional detection methods like signature-based approaches or dynamic analysis demand extensive manual expert effort.
Signatures for known bad stuff.
Right. The problem is they simply don't scale well for the vast number of malware variants we see daily. Attackers are also incredibly adept at using obfuscation techniques like code encryption, reordering instructions, or inserting dead code specifically to evade these traditional defenses.
Making it look different each time.
This is precisely where AI steps in. State-of-the-art research leverages deep learning algorithms combined with both static and dynamic analysis to counter these evasion techniques. Dynamic analysis identifies runtime behaviors, but it needs specific inputs. Static analysis, on the other hand, examines the program's structure without executing it, looking at disassembly, opcode sequences, and control flow graphs.
Analyzing the code itself.
The method introduced in this chapter, demonstrated by Intel Labs and Microsoft, tackles this by converting malware into various data representations, images, sequential data, and graphs. Deep learning is then used to learn subtle similarities among malware samples and, crucially, dissimilarities between malware and legitimate software, enabling robust detection even against sophisticated obfuscation.
Section 6.2 discusses the raw data used to fuel these models. Malware samples are often collected from large public repositories, and external services are used to label these samples and identify their families.
Like VirusTotal.
Exactly. The types of malware include common families like viruses, worms, trojans, ransomware, and adware. For legitimate programs, datasets are typically gathered from official operating system packages or popular open source software.
Moving to data processing, section 6.3. The goal here is to represent malware in a way that AI can understand its malicious behaviors through static analysis, meaning without ever executing the binaries. The chapter introduces 3 powerful ways to represent malware data for AI images, sequences, and graphs.
First, image data conversion. We saw this with DNS, but here it's for whole binaries. Imagine taking the raw binary code of a program, which is just a long stream of bytes, and literally reshaping it into a 2-dimensional image. Each byte becomes a pixel.
Malware is a picture.
This allows us to use powerful computer vision models, like those that recognize faces, to see patterns in the malware structure. It's a surprising yet effective way to leverage existing AI capabilities.
Next, sequential data conversion. This is more straightforward. The binary code is directly converted into sequences of bytes, treated as unsigned integers. Since binary sizes vary, these sequences are partitioned into fixed-length subsequences, with any leftover bytes padded to ensure uniform length.
Treating it like text.
This representation allows AI to look for patterns in the linear flow of the code.
The third representation is graph data conversion, leveraging the control flow graph, or CFG. Think of a CFG as a program's roadmap, a directed graph representing all the reachable paths a program can take during execution.
How the code jumps around.
The nodes in this graph are basic blocks, chunks of consecutive code with a single entry and exit, and the edges represent possible control flows between these blocks.
CFGs are incredibly valuable because their structural information shows the step-by-step execution process. This helps in finding unreachable code, identifying syntactic structures like loops, and even predicting program defects. Tools are used to extract these CFGs and transform them into a graph structure where each node, representing a basic block, has features derived from its byte sequence.
So the AI sees the structure.
This allows the AI to understand the architecture of the code, not just its linear content.
Now for model training, section 6.4, where deep learning architectures are applied for malware detection. Each of the three data representations we just discussed, images, sequences, and graphs, gets its own specialized deep learning model.
Right, tailored models for each view. For image data, CNN models are used, often leveraging transfer learning.
Using models trained on regular images.
Yeah. This is a smart technique borrowed from computer vision, where we apply knowledge gained from models trained on millions of real-world images to our malware images. So instead of training from scratch, we might use a powerful pre-trained network like ResNet 50, which already understands basic visual patterns, and then fine-tune it to recognize malicious code patterns, making the training process much more efficient.
For sequential data, recurrent neural network RNN models, especially LSTMs or GRUs, are employed. These are excellent at learning patterns and sequences.
Like we saw with anomaly detection.
Imagine the AI processing the byte stream of a binary, learning high-level features by looking at how bytes relate to each other over time, effectively learning the grammar of malicious code.
Moving to graph data, graph neural network GNN models are used. These models are designed to directly process graph-structured data. A core component is the graph convolution layer. Think of it like a ripple effect. Each node in the code's control flow graph passes its features to its neighbors, and they combine that information with their own.
Sharing information across the graph.
By stacking multiple such layers, the GNN can build a collective understanding of the code's complex structural features, not just individual nodes.
When we look at model performance, how do these different approaches stack up?
These deep learning approaches, whether using CNNs for images, LSTMs for sequences, or GNNs for graphs, generally achieve very high accuracy in detecting PC malware, often in the high 90th percentile. They also show strong recall and precision, meaning they are both thorough in finding malware and accurate in their classifications.
So they all work pretty well.
These results underscore the significant advances AI brings to this complex problem.
For model deployment, the design of a production system for PC malware detection is similar to what we discussed for Android malware. However, a key difference here is that this use case primarily relies on static analysis, meaning the binaries are analyzed without being executed.
Right, no need for emulators here.
This significantly simplifies the execution environment compared to dynamic analysis, which requires emulators or virtual machines.
Even with good performance, there are always remaining issues, as discussed in section 6.6. Traditional malware detection methods, like signature-based approaches, are effective for known malware but quickly become useless against unknown or obfuscated variants.
The cat-and-mouse game.
Dynamic analysis, while comprehensive, is computationally expensive and slow. Static analysis is faster but can still be challenged by sophisticated obfuscation.
Crucially, even high-performing deep learning models are vulnerable to adversarial attacks.
Trying to fool the AI itself.
Attackers can intentionally modify malware code with obfuscation techniques, like inserting dead code, reassigning registers, or transposing instructions, in subtle ways that preserve the program's original malicious meaning but alter its syntax.
So it still does the bad thing but looks different.
These changes can trick deep learning models into misclassifying malware as benign, much like it evades signature-based detection. This is an escalating arms race.
Let's turn our attention to Chapter 7 now, where AI dives into detecting code similarity. This is a challenging problem with wide-reaching implications for cybersecurity.
Finding code that's the same, or almost the same.
Exactly. Section 7.1 outlines the security problem. Detecting binary code similarity is incredibly useful for many applications. Searching for known vulnerabilities in new software, identifying code plagiarism, and analyzing malware families to see how they relate to each other.
Finding reused code, basically.
But measuring this similarity is tough. Factors like the specific compiler used, its optimization level, and the processor architecture all significantly affect the binary output. This makes it incredibly difficult to generalize code similarity detection, especially across different versions of software or diverse compilation settings.
The same source code can look totally different as a binary.
Precisely. AI promises to overcome these challenges by extracting high-level, abstract representations of the code, which then allows statistical methods to become very effective at discerning true similarity. The core problem definition here is straightforward. Given two pieces of binary code, determine if they were compiled from the same original source code.
Okay, focusing on same source.
Importantly, this doesn't typically cover semantic clones, codes written differently for identical purposes, as those are usually detected at a higher source code level.
When applying deep learning to code similarity, two main types of input data representations are used: a dedicated graph representation and a raw byte sequence representation. This chapter focuses heavily on graph representation, as sequence models are similar to those we've discussed in computer vision, requiring less domain-specific knowledge during implementation.
Section 7.2 discusses raw data and how to generate labeled code pairs. While binary similarity can be measured at different levels, comparing individual functions is most common. The challenge is getting accurate ground truth labels.
How do you know for sure two binaries came from the same source?
The solution for supervised training is clever. You compile the same source code multiple times, but with different optimization levels and compilers. This produces vastly different binary code for the same original function. Identifying these seemingly different binaries as similar is exactly what the model learns to do.
Generate your own dissimilar pairs.
So the raw data consists of binary codes of functions obtained by compiling source code with varied settings. During training, functions are typically identified via symbol tables, and in a real-world production environment, existing tools like ID Pro are used to extract functions from stripped binaries.
Moving to data processing, section 7.3, this is all about crafting these representations for similarity analysis. The goal is to convert raw binary data into representations that can capture subtle relationships for the AI to learn.
For graph representation, traditional methods might abstract program information into control flow graphs, CFGs, and then handcraft statistics about those graphs. But with the maturity of graph neural networks, GNNs, researchers now design graphs directly based on CFGs to serve as input for deep learning models.
Using the CFG again.
The clear advantage here is that structural information is preserved natively, along with other crucial details encoded in the nodes.
The nodes in these graphs, typically basic blocks of code, are represented as fixed-length vectors with selected attributes, often called node features. These features can be derived from expert domain knowledge or generated as embeddings by another model. A prime example is the Attributed Control Flow Graph, or ACFG, where each node has several features. Things like the number of constants, calls, or instructions within that basic block, and even structural features like the number of outgoing edges.
The ACFG is particularly powerful because it's architecturally independent, which helps alleviate the huge challenge of cross-architecture code similarity detection. So a function compiled for by86 might still be recognized as similar to one compiled for ARM, despite looking vastly different at the raw binary level.
That's really useful. Now let's look at the model itself in section 7.4, which is all about learning code embeddings with Siamese networks.
Siamese networks, okay.
The ultimate goal is to obtain quantified similarity scores by learning embedding vectors. Think of it like face recognition for code. Similar binary codes should generate very similar embedding vectors, much like different pictures of the same person yield similar facial embeddings. To achieve this, a popular architecture is the Siamese network.
The Siamese network architecture uses two identical subnetworks that share their weights. Each subnetwork takes one sample from an input pair, for example, two different binary functions.
Two inputs, two identical networks.
The loss function is then based on the distance between the outputs of these two subnetworks. The AI aims to minimize this distance for inputs that are similar and maximize it for inputs that are dissimilar.
Pushing similar things together, dissimilar things apart.
For our graph representation, the backbone of this Siamese network is a graph neural network, GNN. This GNN aggregates node features from a function's control flow graph to create node embeddings, and then aggregates these node embeddings to form a single, comprehensive graph embedding for the entire function. In plain terms, it learns to understand the unique structural fingerprint of each function.
The key idea of the Siamese network is learning from pairs. It uses what are called contrastive losses to handle both similar and dissimilar pairs.
Contrastive loss.
The loss function is designed to pull the embeddings of similar pairs closer together while pushing the embeddings of dissimilar pairs apart, but only up to a certain threshold. This teaches the network what differences matter and what differences are just noise from compilation. Crucially, the two subnetworks share their weights, ensuring they learn the same transformation on both inputs.
Finally, Section 7.5.3 touches on active learning, a crucial technique for efficiently labeling scarce data. Siamese networks, like most deep learning models, require many carefully labeled similar and dissimilar pairs.
Getting that labeled data is the bottleneck.
While compiling the same source code with different settings can generate some data, including examples that are semantically similar but structurally very different at the source code level, can significantly improve performance. But this often requires manual labeling, which is very costly.
Active learning helps make this manual labeling more efficient. Instead of randomly selecting samples for humans to label, active learning identifies the examples where the model is most uncertain or where it thinks it could learn the most.
Focusing the human effort.
For Siamese networks, where the output is an embedding rather than a confidence score, a proposed solution involves using another small subnetwork to predict the potential loss value for a given input. If the predicted loss is high, that sample is selected for human labeling, making the process much more targeted and efficient.
Smart way to prioritize labeling. Okay, Chapter 8 now, where AI conducts malware clustering. This is about managing the sheer deluge of new threats flooding the internet every single day.
Grouping similar malware together.
Exactly. Section 8.1 defines the security problem. Malware is an enormous and constantly evolving threat, with anti-malware vendors receiving literally thousands of new samples daily. While automatic tools can analyze individual samples, this simply isn't enough to manage the sheer scale.
Can't look at every single one individually.
There's a crucial need for prioritization. Security analysts need to quickly focus on novel or particularly critical malware.
The solution is malware clustering. This is an unsupervised machine learning technique that groups malware samples that exhibit similar behaviors.
Unsupervised, so no labels needed initially.
Right. It allows analysts to quickly detect and focus on malware that is either novel and interesting or requires immediate attention because it's part of a new dangerous campaign.
Existing malware clustering methods often suffer from limitations in their ability to cluster related samples effectively, especially for large-scale operations. This chapter's use case, based on a mature research technique, is designed to identify and group similar malware behavior at scale.
Section 8.2 outlines the machine learning pipeline for clustering. This particular approach notably does not utilize deep learning, demonstrating the breadth of AI's application beyond neural networks.
Back to more traditional ML.
It's a three-step workflow. First, analysis gathers information on malware. Second, feature extraction pulls out relevant behaviors from these analysis results. And third, a clustering algorithm groups samples based on these features.
This specific use case employs dynamic analysis, which is often preferred over static analysis because it's better at handling runtime packing, complex obfuscations, and programs that are functionally identical but look different in code.
Running the malware to see what it does.
Taint tracking, a technique that tracks data flow from sensitive sources, is integrated to enrich the information gathered. The output of this analysis is summarized into a behavior profile, which is an abstraction capturing system call-related resources and operations. This profile is then transformed into a feature set suitable for clustering, which is then fed into a scalable clustering algorithm based on locality-sensitive hashing.
Moving to feature extraction in Section 8.4 is all about capturing malware behavior. It's worth noting that building a custom dynamic malware analysis tool is a huge undertaking. The focus here is on using existing tools that can perform this complex analysis.
Right, leveraging existing platforms. A key part of this is dynamic analysis with taint tracking. This approach enriches and generalizes the information collected, displaying malware behaviors in terms of OS objects like files, registry keys, or network connections, and OS operations, generalizations of system calls performed on these objects.
Abstracting the low-level actions.
A behavioral profile is essentially a comprehensive summary of how a malware sample interacts with the operating system, including system call dependencies, control flow dependencies triggered by tainted data, and network activities.
From this detailed behavior profile, features are generated. For example, for every object operation pair like opening a specific file, a unique feature is created. Similarly, features are generated for observed dependencies between system calls and specific types of comparisons involving sensitive, tainted data.
Turning behavior into features.
This translates the complex behavioral profile into a structured, numerical feature set that a machine learning algorithm can process.
Section 8.5 discusses scalable clustering, which uses locality-sensitive hashing, or LSH. The goal is to efficiently group malware samples using their extracted feature sets, even with massive amounts of data.
LSH sounds complex.
LSH is a clever algorithmic technique that hashes similar input items into the same buckets with high probability, making it ideal for quickly finding likely similar data points. The output is a set of candidate pairs of potentially similar malware samples, which can then be used to produce a hierarchical clustering.
Before LSH can be applied, malware samples need to be processed into an input matrix. Each malware sample, represented as a set of features, becomes a column in a Boolean matrix, where a 1 indicates the presence of a specific feature.
Rows are features, columns are samples.
Importantly, features that are unique to only one sample are discarded, as they aren't useful for finding similarities between different pieces of malware.
To measure the sameness between any two malware samples, Jacquard similarity is used. This is a common metric that calculates the size of the intersection of two feature sets divided by the size of their union. Essentially, it tells you how much overlap there is in their observed behaviors, from 0, no overlap, to 1, identical behaviors.
How similar are their feature sets?
For very large, sparse input matrices, processing them directly can be computationally intensive. This is where min-hashing comes in. Min-hashing is a technique that compresses the input matrix into a much smaller, denser signature matrix.
Making it smaller, but keeping the similarity info.
The key property of min-hash functions is that the probability of two sets having the same min-hash value is equal to their Jacquard similarity. So instead of comparing huge feature sets, you compare their much smaller signatures.
Locality-sensitive hashing, LSH, then takes these compressed signatures and efficiently finds candidate pairs of similar items. It does this by dividing the signature matrix into several bands and using a hash function on each band.
Bucketing similar signatures together.
If two samples hash to the same bucket in any of these bands, they become a candidate pair. This process is much faster than comparing every single pair of malware samples directly, allowing for clustering at scale.
For clusters deployment, LSH provides an approximation of true near pairs. So, any candidate pairs whose similarity is actually below a certain threshold are removed. The refined set of candidate pairs is then used to produce a single linkage agglomerative clustering.
Building the clusters up from the pairs.
This means starting with each malware sample as its own cluster and then iteratively merging the closest pairs of clusters until a desired structure is achieved. This typically uses standard machine learning libraries, where you provide a distance matrix Jacquard distance, which is simply one Jacquard similarity, to define how far apart samples are.
Okay.
While LSH focuses on finding only pairs above a certain similarity threshold, an exhaustive hierarchical clustering can still be performed on the cluster representatives and any remaining isolated samples. This is acceptable because, at this stage, the number of items being clustered is usually much smaller.
In concluding remarks for malware clustering for very large data sets, the time complexity of this algorithm can still be high, primarily dominated by calculating the similarity of each pair.
Still quadratic in the worst case, potentially.
This means for truly massive petabyte-scale data sets, more aggressive clustering schemes that might sacrifice some accuracy for speed could be necessary.
A key limitation is also malware evasion. Since features are extracted via dynamic analysis, malware that is intentionally modified to behave differently from others in its cluster will weaken performance.
Attackers trying to break the clustering.
Attackers are constantly evolving, trying to subtly change their code to break existing detection and clustering mechanisms. This highlights the continuous need for system evolution and adaptation.
Wow, what an incredible deep dive we've had today. From teaching AI to reverse engineer binary code and identifying subtle shifts in network activity, to detecting Android malware on your phone and neutralizing insidious DNS cache poisoning attacks.
Categorizing PC malware, identifying code similarity, and even efficiently clustering new malware families, we've seen the sheer breadth of how AI is truly revolutionizing cybersecurity.
It really is vast.
Indeed, it's clear that the systematic approach of the unified machine learning and deep learning pipeline, even with its necessary variations for specific problems, provides a powerful and adaptable framework for tackling these complex challenges.
That pipeline keeps showing up.
From the meticulous process of data processing and feature engineering to the careful selection of appropriate model architectures and the crucial steps of training and deployment, each use case highlights a thoughtful, methodical application of AI.
The insights from this handbook are genuinely equipping. Learning about how raw binary code is translated for AI, the crucial choice of key APIs for mobile malware detection, understanding the bidirectional context of LSTMs for anomaly detection.
How we represent binaries as images for CNNs, or the incredible efficiency of LSH for malware clustering, these details move us beyond simply understanding the headlines.
Right. It's more than just buzzwords.
They empower you, our listener, to critically evaluate and even begin to contribute to the next generation of cybersecurity solutions.
This brings us to a provocative thought to leave you with. As AI becomes an ever more integral part of our digital defenses, how might the continuous evolution of both sophisticated attacks and the AI models designed to counter them shape the future of cybersecurity?
And what new, unforeseen challenges might emerge from this ever-escalating technological arms race between human ingenuity and artificial intelligence?
Definitely something to think about. That's all for this deep dive. If you're looking for more details, the handbook's accompanying GitHub repository is an excellent resource, providing raw data, code snippets, and scripts for many of the techniques we discussed today.
Check it out if you want to get your hands dirty.
Join us next time for more insights into the cutting edge of technology.